Thanks. Is the audio is bouncing? All right, excellent. Dear Father, we thank you for this day. Again, Lord, I thank you for these students. Pray that the snow would start soon. Let it fall fast, quickly, deeply, before too long. In your name I pray, Lord Jesus. Amen. I have my reasons. I think it's gonna be midnight. Oh, I've given up on calc tomorrow almost. I mean, I do have calculus tomorrow, but
Did you already cancel class?
no, I have not canceled class. I'm gonna, the forecast changed dramatically between last night and this morning, so I'm gonna give it a few more hours and see where it goes. Just to be safe. Don't tempt me. Okay, let's get started. So today I'm going to introduce you to a new concept. The new concept we're going to talk about today is important, maybe some people would say more important than other things we've talked about so far, but the concept is anyway what's known as momentum. So momentum is one of the basic physical attributes you can ascribe to a physical object. You talk about the momentum of an object. In the same way you can talk about its mass or its velocity. In particular, if you have a point mass, all right, with say m, and it has velocity with velocity v, all right, then the momentum is a vector and it's equal to the mass times the velocity. Like, okay, well, why bother? Well, I mean, fine. You're just inventing another thing to give yet another way to talk about the same stuff. Oh, okay, fine. That's kind of sort of true. For example, if we look at this mass and we look at the net force on it, what do we have? We've got mass times acceleration, right? Is equal to the net force. What does this look like if we rewrite it in terms of momentum? Well, that's m times what? dv dt, which is what? That's ddt if the mass is constant, right? That's ddt of m times v, right? So, well, this is what? This is dp dt is equal to the net force. So that's kind of pretty. Instead of saying force is equal to mass times acceleration, we can say force is equal to dp dt, where dp dt is the instantaneous rate of the momentum with respect to time. Yeah.
P momentum?
Yes, p is the momentum. Sorry, is called momentum. Duh. It's a vector, all right. What are its units? Of course, when we talk about units, we're talking about the magnitude. Yeah, kilograms times a meter per second. Sorry, it's bothering me the way I wrote that. Kilogram meters per second. There. It's got no name. I mean, kilogram meters per second squared is a Newton, right? A kilogram meters squared per second squared, well, that's a Newton meter. That's a joule. But as far as I know, it's just that. Kind of funny. All right. Anyway, so first thing, I can restate the net force in this way, right? So if it's one, and then you can do what? You can say, okay, so over an interval of time, if I say integrate from time 1 to time 2 of dp dt, what do I get? P of T2 minus P of T1, right? By calculus. This is, you could also say, well, that's the change in momentum over that duration of time, right? This is what's called the impulse. This is the impulse. Right? But just take a step back. If we're talking about the net force, right, on a single particle, then the impulse is also what? It's equal to the integral from T1 to T2 of the net force, right? So the integral of the force is the change in momentum. If the net force is 0, what happens to the momentum? Right, it doesn't change. Of course, you can see that immediately from here, right? If the net force is 0, dp dt is 0, so p is constant. If the net force is 0, momentum is conserved. Anything else we can do here? What other things do we like to talk about before? How about energy? Kinetic energy is what? 1/2 mv squared, right? But you could also write that as 1/2 what? What's the relation between P and M? P, the magnitude of the momentum, is m times v, where v is the speed, right? So speed is actually momentum divided by mass, magnitude, of course, I'm talking about here. Square that thing, what do you got? Nice formula. P squared divided by 2m is another way to calculate the kinetic energy of a particle. If I know the momentum, and if I know the mass, I know its kinetic energy. Of course, you can also play calculus 1 games here, right? Like typical example, I don't know, you've got some graph that's given. Here's time, here's force, and here's some kind of thing. All right, so the area here is 3, the area here is 2, and let's suppose that this is times 7. You can say if the momentum at time 0 is equal to 3 kilogram meters per second, then P of 7 is what? How would you solve this problem? Well, the integral, I'm supposing this is the net force, and we're talking about just one particle at the moment. All right, well, and you know what I'm saying this area this is area 3, right? This area, sorry, this again, as I've mentioned before, these inferior whiteboards and my inability to shade on them worth anything. Disappointing. Sorry. I have no way around it. Integral, well, actually I do. I got a chalkboard in my office now. Integral from 0 to 7, f of t dt is just equal to P of 7. Well, just one step here, okay? This is the integral of dp dt dt from 0 to 7, right? So by net change theorem, that's P of 7 minus P of 0, right? So let's put it all together here. What's the area? And when I say area, I really should say signed area, right? Area above the x-axis, t-axis counts as positive. Area below the t-axis counts as negative. Such is the life of the definite integral. So we have 3 minus 2 is equal to P of 7, which we don't know. Well, we'll know soon. Minus P of 0, which is 3. So P of 7 is what? Four kilograms meters per second. So if somebody gives you the integral, if somebody gives you a graph of force versus time, you can discern from that how the momentum is changing for a one-dimensional system. All right? Does that make sense? Also for a one-dimensional system, if the net force is 0, momentum is conserved. All right? Actually, is that a one-dimensional comment? Not really. This right here, you could do 2 or 3 dimensions just the same, right? Now, for one particle, it's not that interesting. I mean, for one particle, pretty much we're just it's just a new letter, another way of kind of like packaging the mass into something else in some sort of scale factor. I mean, there's not much added to the analysis here, I think. I don't know. I mean, I guess impulse is a useful concept. I mean, it is a useful concept for sure. Impulse is an important idea. But where momentum really shines is when we study systems of particles. Not just a single particle, but a bunch of them at once. All right? So I'm going to trade our single particle for a whole system of n of them. So, and then once I'm done talking about this, then we will, bump it up a notch and go for continuous distributions of smeared out continuous. All right, so there's n of these masses. I don't know how I've got them arranged, just different places, all right? Each one of those masses is at a particular position vector, right? So I pick an origin somewhere, say here, for the purposes of my artistry. And then, you've got the position vector. We can say this one's at R1, right? This one is at R2 relative to some origin. I'm assuming that the origin is fixed. We're taking measurements relative to some some fixed inertial frame. It's not moving. There's this origin that's sitting there somehow. We assume the existence of such a thing. To a good approximation, you can use the fixed stars as a background to set this up, but whatever. We're not going to do that. I mean, just you believe in it. Have faith. All right, so great. And then what we can do is we can ask ourselves, for each particle, we can say Newton's law applies, right? So the question is, what are the forces on the particle? All right, so as you think about these different particles, let's think about the first particle. On the first particle, there is, let's say, different things going on. For one, there's the F, I'm going to put an upper one, if you don't mind, external. There's the external force on F1. This external force, in principle, has nothing to do with the other masses, all right? But then there's also what are called internal forces. Internal forces are coming from these different masses acting on each other. Okay, the difference between internal and external forces have to come in third law pairs. So like, there's also the force of, like here, let's say, I don't know, maybe it's like this. Maybe M2 is somehow pulling on M1. And so we would say that's the force of 1 pulling on 2. Well, other way around. Let's say 2, 1. So I'm going to say that's the force of 2 on 1. It could be that there's little strings that attach them, and you could think of M1 and M2 actually being like little dudes pulling on each other with a string or something. There could be some kind of spring between them. They're pressing on each other with springs. It could be something more ethereal, like they're throwing they've got water balloons full of kombucha or whatever. What's that garbage you guys drink, some of you? Yeah, that stuff. Oh. My wife had that in the refrigerator for a while. I'm like, why? What's that? Sorry. I don't know. It just doesn't seem right. Now, Newton's third law says that for every action, there's an equal and opposite reaction. So in particular, it says that the force, there's also a force of 1 on 2, force of 1 pulling on 2. And the relation between these is what? They're equal, but they're opposite in direction. That's a third law pair. Well, there's also what? There's a bunch of forces on M1 in principle, right? There's the force of, there's also, like the force of 3 on 1, right? And so forth, right? These are not in any particular direction. The only reason I'm writing them in the direction that they're in is for the purpose of me being able to write them without overlapping the symbols. This picture is a heuristic guide for what's going on. When you look at the nth particle down here, what do you got? You've got like the external force on the nth particle, right? And then you've got, what do you got? You got, the force of 1 pulling on the nth particle, right? And the force of the second one pulling on the nth particle, all the way on to the force of the n minus 1th one pulling on the nth particle. Do you guys understand the setup? No? What in particular?
I don't understand it well enough to say that I don't understand.
Oh, okay. That's fair enough. Yes, sir.
For the, you say you just put the force directions in anywhere so you can just fit them on there?
Yeah, just for the picture. I don't mean to actually say, I mean, more often than not, what actually is going to happen is the forces are going to be, are going to be along the line which connects the two masses in that direction. That's usually what the case will be. But I suppose you could imagine that M1 has a bat, and it's hitting M2 in the side of the head, like that, and then the force would be that way, but yeah.
So are those all 4 different masses?
There's N of them. There's a dot here. I can't, I'm not good at drawing N, so I drew 4.
I was confused because I thought it was like one mass that was showing was like rotating on an axis or something, and those are the different positions.
Well, these could be going all kinds of different which ways. One could be going up, one could be going over. I haven't even said anything about which. I mean, they're not fixed in place or anything like that. These are free to move around. Look, we can make it a little bit more concrete here. So if you look at M1, and if you look at the acceleration of the first one, right? Which, by the way, would be what? That would be M1 d squared R1 dt squared, right? What would that be equal to? Well, that would be equal to the sum of the forces on M1 by Newton's second law, right? We can just write it symbolically as sum of all forces on M1, right? Now, what is that actually? Of course, on the one hand, you've got the external force. And I'm lumping all the external forces together. Maybe there's a gravity force. Maybe there's a wind blowing on these, and they've got little sails. That would be another external force. I'm not thinking of the wind as part of the system. We got all kinds of things. Yeah.
How is one of them pulling on the other, not an external force?
I'm saying everything. It's a definition. I mean, the external. What I'm saying. The system. All right. So I'm trying to introduce you guys this idea. The system includes M1, M2, Mn. That's it. Okay. So those masses and the forces created by those masses on each other, those are internal forces. Anything from outside that is an external force. The demarcation of internal and external is somewhat arbitrary. I'll shut up about that. But okay, then plus what? Then plus the sum, right? In this case, I equals 2 to n, right? Of what? F. What do you got here? What do those look like? In my notation, it's always 1, right? So it's like I, comma 1, right? And then we can look at Newton's second law for the second mass. We'd have M2, A2, right? M2, I guess I could use this notation, R2 prime prime. That would save me some writing. Well, that would be equal to, again, the sum of all the forces. I'm just doing this so it lines up. Sum of all the forces on M2, right? In particular, there's the external force on 2, right? Plus what? Plus the sum. Well, now we've got what? It's a little bit sneakier. Let's see here. I not equal to 2 to n, right? F I2. There's a sneaky way of writing the sum from 1 to n, just not including 2. Do you understand the notation? I'm saying that sum is taken over 1, 3, 4, 5, 6, 7, n. Everything except for 2. You say, what about the force of 2 on 2, right? Well, I sat for, I was in a junior level, I transferred from community college to NC State back in the day, and I sat in junior level classical mechanics one day, and I well remember this story, because there was a student who wanted to argue with the professor about this, basically. And the professor told him, well, if you think a mass can put a force on itself, then you go ahead and do it. Reach down, put your fingers under your toes. I probably can't do it. Yeah. And then just pick yourself up off the ground. What's the problem?
Gravity's really.
Yeah. No, we don't. A mass can't put a force on itself. So the nth mass times the nth acceleration would be mn r prime prime n, and that, of course, will equal the external force on the nth particle plus the sum I not equal to, I guess this one I can say I not equal to n, right? But to be more precise, I could just say I equals 1 to n minus 1 in this case, right? F I comma n. All right. Yes, sir.
One question on the mass not putting a force on itself.
Mm-hmm.
Like, how do you know where to draw the line of what defines that mass? Because I could punch myself in the head and apply a force that would cause my head to move, so that in that instance, my hand would almost be a separate mass from the head.
Ah, yes.
But in the
But
case of picking yourself up, your whole thing is the mass. So
But these are point particles. So point particles don't have hands. So, but yes, in fact, you're a system. So when you punch yourself in the head, your head is also punching your hand back. There's an equal and opposite reaction there, right? Yeah.
Does that mean that the force exerted on itself would just be 0, so you could include it? Because it wouldn't change.
If you want to say that the force of anything on itself is 0, I can't disagree with you. Sure, why not? In the same sense, we can say every cat gives birth to dragons and other things like that. It's just that there's 0 of them, right? So, I don't know. I mean, yes and no. It depends on what you mean. I'm sorry. I just when I say that there's no a body can't put a force on itself, I'm talking about, of course, a closed system, right? Where there's no way you can somehow put an external force on yourself through some chicanery. So there are parameters here to this discussion. But a good example of that would be just a person sitting, or a couple people sitting in like a one of those wagons that you pulled around as kids, right? And on a frictionless surface, there's no way that you can make the wagon go a particular direction. Because you can't put an external, I mean, if you can't put an external force on it, you can't change the net momentum of it, so you can't move. Well, anyway, I digress. So, so here, I could do another thing, right? I could also write this in terms of what? I can either write it like this, that's fine, right? But there's another thing I could have done. And let me do this manga style if you guys don't mind. This is what? This is also dp1, right? dt, this is dp2 dt. This is dpn dt, yeah? Where I'm defining what? Just that, I mean, it's pretty much implicit with what I already wrote. It's the jth momentum is the jth mass times the jth velocity, right? Momentum of the jth particle. So what do you think I'm going to do now? I'll tell you what I'm going to do. I'm going to add these equations. Don't tell the other math professors I did this. Okay. So what happens when you add the momentums? P1 plus P2, right? Plus Pn. Right, because the sum of the derivative is the derivative of the sum. Still true for vectors. Then what? What else can you say? What's this equal to? See, these guys come in third law pairs. So when you add all of these up, all those internal forces do what? Yeah, they be canceling. So these horrible things all die. They'll cancel each other out, and you're just left with the sum of this, this, and that. In other words, the net external force. And we usually just call this the external force on the system. It's just the sum of the external forces on all the constituents of the system. What happens if the net external force is 0? Then the sum of P1, P2, P3, Pn is also constant. In other words, momentum is conserved for the system if the external force on it is 0. Now this thing is so important that it has a name. This is just called the net momentum, or just P for short. Tell you what, I'll make it a capital P. Net momentum. Now, if I write this, this is what? This is also m1v1 plus m2v2 plus plus mnvn, right? Yeah, so it begins. Now I didn't do anything. That's what its definition is, right? You can define, right? You can define something called the center of mass. And let's see here. So basically, what you want is you want the center of mass to be sort of like where all of these things are collectively found. So I don't know, I'm a little bit how to define it. I mean, I could define it first and then show you something here, or I could tell you, I'm going to take this a viewpoint today. It's kind of like chicken or egg. But basically what you want here is you want this to be the total mass times, let's say, the velocity. Usually I use a big V, the velocity for center of mass. Where here V is equal to dr dt. I'm using a big R for the center of mass. So what would that suggest? I mean, if you know this, basically if you want this to be true, it forces you to define the center of mass to be as follows. I'm running out of space. Let me do it over here.
Professor, what is capital N and capital V?
Hmm?
What are the capital M, capital D mass?
I'm defining them. Maybe fine here. Let me just. It'll be easier to follow if I do this. Definition. Capital M is the total mass. All right. R is the center of mass. That is 1 over the total mass times M1 R1 plus M2 R2 plus Mn Rn. This is the so-called center of mass. And I'd like to say it's a weighted average, but that doesn't seem right until I do this. Now it's literally a weighted average. Yes, sir. Center of mass for the system, yeah. Well, same thing as center of gravity. Yeah, I think so. I think that's correct. Let me erase these silly. I mean, you can erase the g's if you want. The point is it is a weighted average. In fact, the heavier something is, the more it contributes to where the center of mass is, right? So yeah, I guess sometimes it's called center of gravity, but I call it center of mass. To me, mass is primary. Okay, and then if you differentiate this, right? That gives you the velocity of the center of mass. And you can see what that is, right? This is a constant, right? So you just have what? You've got 1 over m, right? m1 v1, mn vn. Do you see that? Just differentiate this, ignore the g's. You get dr1 dt, dr2 dt, drn dt. Those are the velocities of the first, second, the nth particle. So this is the relation, this is the velocity of the center of mass as it relates to the velocities of the constituents of the system. And then, of course, you see this calculation I did over here, right? This calculation I did over here in terms of the initial, the positions, velocities, accelerations, and individual momentums of the system, it really just boils down to the following statement, that dp dt is equal to the external force, where p, of course, is what? The total mass times the center of mass velocity. In other words, what I've just derived for you is that for a system of particles, right, it's as if they're a single particle at the center of mass, right, where the net force exerted on that particle is the sum of the external forces which are exerted on the constituents of the system. That's the beauty of momentum, is it allows us to trade a system of particles, which is kind of complicated, for a single particle, conceptually, at the center of mass. That's cool. Now, of course, there's other things, like we can work collision problems. So I'll do some of those now. Any questions, though? A collision. What is a collision? I would say, roughly speaking, you could define a collision as, I think of it as this. I mean, it's an interaction between several bodies, several masses, such that the time of the interaction is so short that there's not enough time during that interaction for external forces to change the momentum. So in a collision, almost by definition, momentum is conserved. So, So basically, some masses collide. Sorry, that seems like a little bit of a circular definition, but you know what collide is, right? Like I do it sometimes, like this. It was for a good cause. I've never broke a classroom before. It's new. I'm sorry that one of you just did that. Off camera. Oops, no. Okay. Masses collide over short time, delta t, right? So momentum conserved is the main idea here, okay? So here's a pretty standard example. You've got car, it's going 30 meters per second. You've got bus going, I don't know, 100 meters per second. Probably not very, okay, fine, that's really not very, I'll do 10 meters per second, I'll be responsible. And then you know the mass. Like suppose the car has a mass of like, I don't know, say 2,000 kilograms. Say the bus has a mass of, I don't know, say 6,000 kilograms. All right. They come to this intersection at the same time. They collide. They stick together in some sort of bus car conglomerate. All right. They smash. They get stuck together, and then they go and they start skidding off here at some angle with some initial speed v naught. So what's the angle and what's the initial speed? Of course, what happens is after the collision, right, which happens pretty quickly, then they skid, maybe they'll skid together, and the force of friction, right, on the tires or maybe whatever else is hitting the road at this point, will stop the thing. But that's an external force on the car bus system, right? Is the idea. So we don't care about that at the moment. We're just asking the question: what's the initial velocity and angle given this? So what you do? Let me give this a name. Let me say this is A. Let me say this is B. All right. So m, the momentum for A plus the momentum for B. These are vectors. If I communicate anything else to you today, if there's one thing that you hear today, hear this: momentum is a vector. Okay? If you ignore that, you simply cannot do these problems correctly. Okay. And then you have the, well, car bus system, right? So mass, so you get like MA plus MB times the velocity right after the crash. The reason these are conserved, right, is because you can think of the car and the bus essentially as a closed system. I'm assuming that they don't speed up, slow down. They're not braking. There's no other way they have to change their momentum before they hit each other, all right? We're neglecting all those other things. Of course, in a real collision, right, you'd have to think about momentum being removed from the car by it braking, hopefully, you know, stuff like that. Okay, so what is this? Well, this is, we got what, 2,000? What's the A velocity? It's 30, 0, plus 6,000, 0, 10, right? let's see, we got 8,000. We're assuming that mass is conserved in this process. V naught x, V naught y. And I can solve that. It's not hard. So this is, whoa, 60,000. Oh man, that's too easy. That was not on purpose. I accidentally gave these the same momentum in magnitude, right? They both have 60,000. This one has a smaller mass but a larger velocity. This one has a larger velocity but a smaller mass, but they have the same momentum magnitude. Direction is different, of course. So that's equal to 8,000. V naught x, V naught y. So what does this tell us? The velocity is actually equal to, looks to me like, good grief. What's 60,000 over 8,000? $7.5? Is it 7.5? Yeah, 7.5. 7.5. And let me care about units finally. Meters per second. This was all done in time, in seconds and kilograms, right? Meters per second. Okay, so what's the angle? Yeah, theta is 45 degrees. And V naught is what? 7.5 meters per second times the square root of 2, which is what, like, I don't know. This isn't calculus 2, so that's not the answer. All right. Remember, I'm just Mr. Cook in here. I'm not Dr. Cook. I don't know about highfalutin, fancy exact answers in here. We want decimals. What's that?
Why do you have the angle is 45?
Yes, y indeed. 10.61 meters per second would be the initial velocity. Because it's the same, its x and y components are equal. So that's 45. Yeah. Does that make sense? Now, Dr. Scamborda says what he likes to do is to take this road and instead put it at like an angle and put the car like this, but make this angle like 20 degrees or something, you know? Then it's more fun. Yeah. But you could do that, right? If I gave you that problem, it wouldn't be much different, really. How would that be different if we put the car, instead of the intersection being at a right angle, suppose the intersection was at a 70-degree angle? How would this analysis change, if at all? Oh, did you guys get that? What was it? I forgot now. If instead we had, yeah, this question? Oh, okay. If I had like this, you know, same everything, except just different angle. So we still have, in other words, I'm still assuming that the bus and the car have the same magnitude of momentum, but now they're not in perpendicular directions. Well, if that was the case, what I'd have to do, right, is I'd actually have to think about the momentum, right, the momentum of the, what did I call it, PA, in this case would be, well, what I do is I would take my 60,000 kilograms, that's the meters per second, that's the magnitude, right? And I would just multiply it by the appropriate unit vector. That's personally how I do it. What unit vector points in this direction? Like, remember geometry? Parallel lines, alternate interior angles, equal 20 degrees. So I can use myself, I can do cosine 20 degrees, sine 20 degrees, that'll do it for me. And now I have to add that to this 0, 60,000. And I won't get 45 degrees anymore, right? Because some of the momentum of the car in this later scenario, some of the momentum of the car is vertical. So there'll be more vertical momentum in the result of the crash than horizontal. The angle will be above 45 degrees. Anyway, I'm bored of this example. I'm going to do another one. The way this cancels conceptually is very nice, because these sums are very worrying when you write them. It seems very complicated. It seems like there's no hope of figuring anything out about them, and yet it's so simple. Another example I'm fond of, I mean, we can do collisions. I think I'll do more collisions another day. I'm tired of collisions for today. Fine, let me do a simple example, really, really simple one. Ice. I don't know. Trump. And then you've got Rubio. I don't know. Why not? And then Rubio crashes into Trump. Rubio has an initial speed of 100 meters per second. Trump has a mass of, let's say, 150 kilograms. I don't know. I have no idea. Rubio, probably 50 kilograms. He's a lightweight. You know it. We've heard it. Trump is initially at rest. All right. So afterwards, what happens? Suppose they stick together. Actually, let's not suppose they stick together. All right. Suppose afterwards, Rubio is going this way at, let's say, 10 meters per second. All right. Then the question is, what's the final velocity of the Trump? Okay, so the point of this is a collision, momentum is conserved. So we and it's one-dimensional, right? So all this pesky components and vector addition stuff goes away, and we just make a convention that right is positive and left is negative, right? So I have something like this: the mass of Rubio, the velocity of Rubio initially, plus the mass of the Trump, plus the velocity of the Trump initially, must be equal to the mass of the Rubio, the velocity of the Rubio at the end, plus the mass of the Trump, the velocity of the Trump at the end. And then we just put in pluses and minuses to the velocities according to the direction. This is my convention. So the V could be plus or minus depending on left or right. So let's see here. Let's do it. We have what? We have 50 times 100. Why is it plus? Because it's going to the right, right? Technically, yes, kilogram meters per second. It just gives me no joy to write that 30 times. If they paid me more, maybe I would include units. Sorry. I just, you know, there's no joy in this job unless I can at least confuse you. So if I can confuse you by not writing units, then all right, sorry. And then what? Minus 50 times what? 10, right? So Rubio has like 5,000 kilogram meters per second momentum to the right before the collision. Then after the collision, he's got, you know, minus 500 kilogram meters per second. 500 kilogram meters per second to the left. Right? After colliding with Trump, Rubio has moved to the left. Okay. Huh. Interesting. Let's see here. 150. 150. Oh, and then what we don't know. All right. And then you solve for the Trump velocity, the final Trump velocity, which is what? VTF is, by algebra, 5,500 divided by 150 meters per second, which is going to give me what? What is it? 36.6? 66? Is it what? Is it 6.7? Should I round this up or round this down? Oh, 6 repeating, so wherever you want to stop it. I know some of you want me to stop it there, so I will. I'm sorry? Ah, yes, good question. Why is there no momentum from the Trump at the start of this, before the collision? Right, this is 0. It's at rest. That's why I didn't write anything there.
His
Yep.
question was, why is it in R instead of 2?
Oh, I'm sorry. I for some reason can't hear you when you speak in here. I don't know what it could possibly be that's keeping me from hearing you. There, but yes, that's supposed to be T. Thank you. All right, a little bit of terminology. Standard test question, something like this, followed by this other question, which is, can you say if was this collision elastic or inelastic? Elastic. What is an elastic collision? Elastic means kinetic energy conserved. So that means the kinetic energy before is equal to the kinetic energy after. For the system. What's the kinetic energy for a system? It's the sum of the kinetic energies of the masses. Okay? And then if the kinetic, if it's not an elastic collision, not elastic is equal to inelastic. All right? Little terminology there. You need to learn it. So is this collision elastic or inelastic? What's the kinetic energy before? One half mass of the Rubio times the speed of the Rubio squared. How much energy does the boy wonder have? What we got here? 1/2 50 10 meters per second squared. what we got? I already know it's inelastic. All I have to do is look at it and go, 100 minus 0 is 100, but 36.67 minus 10 is 46.67. 46.67 is not equal to 100. It's not elastic. That, I'm using a theorem that I'll derive for you, maybe today, maybe some other day. Maybe not today, I don't know. All right, 0.5 times 50. There's a trick for one-dimensional systems to tell if it's elastic or inelastic. Something called if the relative velocity is equal to if the initial relative velocity is equal to minus the final relative velocity, then it's elastic. And only then is it elastic in the one-dimensional case. 250,000 joules, which is less impressive if you call it 0.25 megajoules. Okay, there you go. And then what do you got? This is how Trump would portray it. He's only got 0.25 megajoules. Lightweight. One, but on the other hand, most of the energies with Trump, as you can see, Trump has like he's probably got like 100,000 joules afterwards compared to Rubio's stupid 0.25 megajoules. Sad. Pathetic. Loser. Let's see here. Okay, in other words, that's 0.1 megajoules, basically. As you can see, we lost energy in this collision. This is how typical collisions work. Typical collisions, in the process of the colliding, there's there's maybe noise that's produced, there's heat that's produced in the deformation of the bodies as they collide, and other things like that. And what? And walls. Okay. And so kinetic energy is typically lost in collisions, in real physical collisions. Counterexamples to that, well, the principle, like the quintessential example of something which is not like that is billiards. So in pool, the balls behave essentially like spherical springs, and they as they hit each other, they actually compress and then spring back to their original shape in a very efficient way, such that almost no energy is lost in a hypothetical collision of pool balls. I don't know how true this actually is. It's pretty close to true, though. Collision of pool balls is more like is a good thing to think about if you want to think about what does it mean for a collision to be elastic. When I think of an elastic collision, I'm thinking of something that's very bouncy, right? The farthest from elastic would be a purely something where they stick together. Like this collision of the car and bus is kind of the most extreme inelastic collision that you can think about. It's just they just stick together. That's far from elastic. So, I still have time. Cool. All right. I guess I can derive for you what I'm telling you is there's a little theorem for the change in relative velocity before and after. Let me see if I can derive that for you right quick. Actually, your choice. Do you want me to do that derivation today? Or I could show you an example. We could work the example of something with projectile motion, and then there's an explosion at the top. Your choice. The explosion? All right. I figured you guys would pick that.